there's a line in the rock, it is thin. In most places, it is no more than a centimeter thick, sometimes less. It runs around the entire planet, through the chalk cliffs of Denmark, through the limestone of Spain, through the shale of New Mexico, and the Badlands of Montana, through the deep sea sediment cores pulled from the floor of the Pacific and the Atlantic and the Indian Ocean. Everywhere scientists have looked for it, they have found it. A thin, dark, chemically distinct layer of clay laid down simultaneously around the entire Earth approximately 66 million years ago. Below this line, dinosaurs, ammonites, mosasaurs, pterosaurs, the full, extraordinary diversity of the Mesozoic world. Above this line, none of them. Gone completely and permanently, replaced over the following millions of years by the mammals and birds and the new world of the Cenozoic era. Scientists call this the KPG boundary, the Cretaceous Paleogene boundary, and it is one of the most precisely dated and most thoroughly studied geological events in the history of Earth science. The thin, dark layer that marks it is enriched in iridium, a metal rare in Earth's crust, but abundant in asteroids, and it contains shocked quartz, tiny glass spherules formed by the instantaneous melting and resolidification of rock and microscopic remnants of a catastrophe so sudden and so total that it registers in the rock as a single instant of geological time. The line is not a mystery. We know what caused it. We know when it happened. We know, with a precision that would have seemed impossible to scientists of a generation ago, the exact sequence of physical events that followed the moment of impact. We can reconstruct from the physics and chemistry and biology preserved in the rock what happened in the minutes, the hours, the days, the months, and the years that followed. This documentary is that reconstruction, not a dramatization, not a speculation. A careful evidence-based account of what the science tells us about those final days. The last days of the dinosaurs and the first days of the world we now inhabit. It is a story about ending, but it is also inevitably a story about beginning, because the world that emerged from the catastrophe of 66 million years ago is the world we live in. The mammals that survived the extinction became the elephants and the whales and the primates. The birds that survived became the 10,000 species that filled the sky today. The world as we know it, every landscape, every ecosystem, every living thing on Earth is the direct product of what happened in the hours and days and years after the impact. We owe our existence to a catastrophe. That is an uncomfortable thought. It is also the truth. And the truth, as always, is more interesting than any alternative. To understand what happened 66 million years ago, we need to spend a moment with the world that existed before, the world that was about to end. The late Cretaceous period, in the final million years before the impact, was by almost any measure one of the most biologically productive and diverse periods in the history of terrestrial life. The continents were not in their modern positions. The Atlantic Ocean was narrower. India was an island continent moving rapidly northward. Antarctica was still connected to South America, but the general geography was recognizable. North America, South America, Africa, Eurasia. Each of these land masses harbored its own distinctive fauna, its own assemblage of species shaped by millions of years of isolated evolution. On the landmass we call Laramidia, Western North America, the fauna was dominated by the animals that paleontologists know most intimately. because their fossils are preserved in extraordinary abundance in the rock formations of Montana, South Dakota, Wyoming, and Alberta. This was the world of T-Rex, of Triceratops, of Edmontosaurus and Ankylosaurus, and Pachycephalosaurus, of Quetzalcoatlus, the pterosaur with a wingspan of 10 meters that soared above the western interior seaway, of the crocodilians and turtles and lizards and early mammals and birds that occupied the lower levels of a complex, multi-layered ecosystem that had been developing for tens of millions of years. The Hell Creek Formation, the geological unit that preserves the richest record of this final world, represents roughly 1.5 million years of late Cretaceous time in what is now the northern Great Plains of North America. It preserves forests of broad-leaved flowering plants interspersed with conifers, river systems winding through subtropical lowlands, swampy margins along the shores of the retreating western interior seaway. The climate was warm, significantly warmer than today, without permanent polar ice. And the seasons, while present, were less extreme than those of the modern world. It was a world at the peak of its complexity, the ecological relationships that structured it, the predator-prey dynamics, the competitive interactions, the mutual dependencies between plants and animals, the soil, microbiomes, and the nutrient cycles had been developing and refining for millions of years. It was not a stable world in any permanent sense. It never is for any ecosystem, but it was a mature world, a world that had found its rhythms, and it was about to be ended in a matter of hours. The object that ended it had been traveling through space for most of the history of the solar system. It was a rocky body, a carbonaceous chondrite, or a siliceous castride, depending on which interpretation of the available evidence you favor, approximately 10 to 15 kilometers in diameter. A mountain. Moving through the darkness of space at roughly 20 kilometers per second on an orbital trajectory that had been its path undisturbed for millions of years. It was not the first time something like it had threatened the Earth. The solar system is full of debris, the remnants of planetary formation, the fragments of collisions between larger bodies, the rocks and ice and dust that drift through space on their own trajectories, occasionally intersecting the orbits of planets. The Earth has been struck before many times by objects of various sizes. Most of these impacts were ancient, confined to the first billion years of the solar system's history, when the density of debris was far greater than it is today. But impacts have continued throughout geological time, and the Moon's surface, which lacks the erosion and tectonics that erase impact scars on Earth, preserves a record of bombardment that tells us the solar system has always been a dangerous place. The object that struck 66 million years ago was large, unusually large for the modern solar system. An object of this size hitting the Earth today would be an event without historical precedent in human experience, without precedent, arguably, in the entire span of human civilization or of any of our ancestral species. It was, in the language of risk assessment, an extremely low probability event. The probability of an object this size striking the Earth in any given year is vanishingly small, but 66 million years is a long time. Long enough for a vanishingly small annual probability to accumulate into a near certainty. On a day in the late Cretaceous, a day that was, by all available evidence, an ordinary day in a world that had known nothing but ordinary days for millions of years, the trajectory of the asteroid and the trajectory of the Earth converged. Let us set the scene as precisely as the science allows. The date in our calendar would have been approximately 66,033 years ago, a meaningless number in any human sense, but a fixed point in geological time, established by radiometric dating of the impact layer with a precision of plus or minus 32,000 years. The season, based on analysis of fossilized fish from a site in North Dakota called Tanis that appears to preserve the immediate aftermath of the impact, was late spring or early summer in the northern hemisphere, a conclusion drawn from the growth rings preserved in the bones of fish that died in the impact's first hours. The location of the impact was what is now the Yucatan Peninsula of Mexico, then a shallow carbonate platform covered by warm tropical sea, the Chicxulub crater, as it is now called, named for a small town in the Yucatan near the center of the impact structure, is approximately 180 kilometers in diameter, making it one of the largest impact structures identified on Earth. It is buried beneath kilometers of more recent sediment, invisible at the surface, detectable only by the gravitational anomalies and seismic signatures that reveal its buried geometry. The shallow carbonate platform that the asteroid struck was built from limestone and anhydrite, calcium carbonate and anhydrite. When these rocks are vaporized by an impact, they release enormous quantities of carbon dioxide and sulfur dioxide into the atmosphere. This is not what would happen if the asteroid had struck a different part of the Earth, a granite craton, say, or the deep ocean floor. The specific chemistry of the Yucatan target rock contributed substantially to the severity of the environmental consequences. The angle of impact, estimated at approximately 45 to 60 degrees from horizontal, also mattered. A steeper impact would have generated a different pattern of ejecta. A shallower one might have distributed energy differently. The oblique angle at which the Chicxulub impactor struck appears to have directed the most intense blast of superheated ejecta in a specific direction, roughly northward and northeastward, which is consistent with the distribution of particularly severe extinction signatures in North America compared to some other parts of the world. The time of day, morning in the Western Hemisphere, as the sun was rising over the impact site, is another detail that the physics of orbital dynamics allows us to constrain. The geometry of the asteroid's approach trajectory suggests a daytime impact in the Western Hemisphere, which means the blast effects were directed toward a hemisphere in full sunlight, with the atmosphere heated and convecting in conditions that may have maximized the spread of the initial thermal pulse. All of these details matter, not because they change the fundamental outcome. The impact was going to be catastrophic regardless of these specifics, but because they affected the precise distribution and timing of each phase of the disaster. The story of the last days of the dinosaurs is, in part, a story about the physics of an event of unimaginable scale playing out across the surface of a living planet. The dinosaurs did not know it was coming. This seems obvious, but it is worth dwelling on. The asteroid approached from space, from above, from outside the atmosphere, from a direction that no ground-level organism could detect until the very last seconds. There was no warning. There was no signal. There was no way for any organism on the surface of the Earth to know that anything unusual was about to happen. On the morning of the impact, the dinosaurs of the Hell Creek ecosystem were doing what they always did. A herd of Edmontosaurus was moving through the riverside forest in the early morning light, feeding on the low-growing vegetation at the forest's edge, their broad bills working through the ferns and flowering plants with the methodical efficiency of large herbivores following their caloric imperative. A triceratops was moving slowly through the open ground near a river bend, pausing occasionally to lift its massive head and scan the surroundings, its three horns gleaming in the morning light. Somewhere in the forest margin, the enormous form of a T, Rex was at rest, warm, breathing slowly, the night's hunt behind it, and the day's warmth not yet sufficient to motivate movement. Birds, real birds. The survivors of the Cretaceous dinosaur radiation that would carry the lineage forward through the extinction moved through the canopy above, calling and feeding in the morning cool. Pterosaurs circled lazily above the river, their enormous wings catching the thermals beginning to rise from the warming ground. In the river itself, fish schooled in the clear water, feeding on aquatic invertebrates, and a large crocodilian lay motionless near the bank, its body absorbing the heat of the morning sun. It was, in every observable respect, an ordinary morning, a morning like millions before it. And then, to an observer looking upward in the right direction, a light appeared in the sky. The asteroid entered the Earth's atmosphere at approximately 20 kilometers per second, roughly 60 times the speed of sound. At this velocity, the friction with air molecules is so intense that the asteroid was not simply slowed, it was heated. The surface of the object reached temperatures of tens of thousands of degrees in the first seconds of atmospheric entry. The shock wave compressed the air ahead of the rock with such force that the air itself became incandescent, a plasma, glowing at temperatures comparable to those of the surface of the sun. To an observer within visual range, anywhere within perhaps 1,000 kilometers of the entry point, the approaching asteroid would have appeared as a point of extraordinary brightness, brighter than the sun, expanding rapidly over the course of perhaps 30 to 40 seconds from a point of light to a growing fireball that illuminated the entire visible sky. In those 30 to 40 seconds before the asteroid reached the ground, the thermal radiation from the fireball was already delivering an enormous pulse of heat to the landscape below. Not enough at this point to ignite most vegetation, but enough to warm the skin, enough to be felt. The birds in the Hell Creek forest may have stirred in alarm at the sudden intensification of light. The Edmontosaurus herd may have lifted their heads from their feeding, registering something unusual in the quality of the light around them. The asteroid reached the surface of the Earth approximately 1.3 seconds after entering the atmosphere, traveling so fast that the atmosphere barely had time to do more than heat it. At the moment of impact, the sequence of events that would end the Mesozoic era began. The impact. It is almost impossible to communicate the scale of energy released at the moment the asteroid struck the shallow sea of the Yucatan. Numbers help, but numbers at this scale lose their meaning quickly. The energy released was approximately 100 teratons of TNT, roughly billion times the energy of the atomic bomb dropped on Hiroshima. More energy released in a single second than the entire energy output of the sun striking the Earth's surface over several months. What this energy did physically is somewhat easier to describe. The asteroid drove into the shallow water and the limestone beneath it at full velocity. In the first fraction of a second, both the asteroid and the target rock were compressed to pressures far beyond what rock can withstand. They were not simply deformed or fragmented, they were vaporized. The rock and the asteroid became plasma, a gas of individual atoms and molecules at temperatures of tens of thousands of degrees, expanding outward from the impact point at velocities that exceeded the speed of sound by orders of magnitude. This expanding plasma drove a shock wave through the surrounding rock that propagated outward at kilometers per second. The shock wave liquefied and then shattered the limestone of the Yucatan platform, excavating a crater approximately 100 kilometers in diameter, within the first few minutes. The rock that had been below the impact point was not simply pushed aside. It was melted, vaporized, thrown upward and outward with the energy of the initial explosion. A column of vaporized rock and superheated gas rose from the impact site, punching through the atmosphere and into space at velocities exceeding Earth's escape velocity. This material, tiny droplets of molten rock, glass beads formed from the instantaneous melting and solidification of target rock, dust, and gas, spread above the atmosphere and began to fall back around the entire planet. Within 15 minutes of the impact, the ejecta had spread through the upper atmosphere over the entire hemisphere facing the impact. Within an hour, material was reaching the far side of the planet. Within a few hours, the entire Earth was receiving a rain of superheated particles returning from space, not a gentle rain, but a bombardment of material re-entering the atmosphere at high velocity, converting their kinetic energy to heat as they decelerated through the upper air. The sky was on fire. Day 0. The first minutes. The impact happened at approximately what is now 9 o'clock in the morning, local time, in the late Cretaceous, Yucatan. Within the first 60 seconds, a sequence of physical events was already unfolding that would, in the following hours and days, affect every living organism on the surface of the planet. The first effect, and perhaps the most immediately dramatic, was seismic. The energy of the impact propagated through the Earth as seismic waves, earthquake waves of a scale that dwarfs anything in recorded human history. The moment magnitude of the impact-generated seismic event has been estimated at approximately magnitude 11 or greater on the modern scale, an earthquake roughly 1,000 times more energetic than the most powerful seismic event ever recorded by human instruments. These seismic waves traveled outward from the impact site through the body of the Earth at several kilometers per second. They reached the western coast of North America within minutes. They traveled around the globe and back and around again, the Earth ringing like a struck bell for hours after the impact. Every fault system on the planet was activated simultaneously. Volcanic calderas that had been quietly building pressure for centuries vented suddenly as the seismic waves disrupted their underground plumbing. Landslides cascaded down mountain slopes. The solid rock of the continents shook with a violence that would have been instantly lethal to any organism standing on unstable ground near major fault systems. In North America, approximately 3,000 kilometers from the impact site, the seismic shaking arrived within minutes. The intensity at this distance has been estimated as equivalent to a magnitude 9 or 10 earthquake, again beyond anything in the historical record of human civilization, comparable to the very largest earthquakes the Earth's tectonic system naturally produces. The Edmontosaurus herd on the Hell Creek floodplain would have felt the ground move beneath them, not gently, violently. The riverbanks would have slumped and collapsed. The trees of the riverside forest would have swayed and some would have fallen. The herd would have scattered, the instinctive response of prey animals to anything that disrupts the ground beneath them. The movement that in a normal world would take them away from danger. But this was not a normal world, not anymore. The site known as Tanis in North Dakota is one of the most extraordinary paleontological discoveries of the early 21st century. It is a fossil deposit that appears to preserve the immediate aftermath of the Chicxulub impact, not in geological time, not over thousands of years, but in the hours and minutes of a single day. Tanis was first described scientifically by a team led by paleontologist Robert De Palma, with a paper published in 2019 in the Proceedings of the National Academy of Sciences. The site preserves a remarkable assemblage: fish, paddlefish, and sturgeon, buried in freshwater sediment in poses consistent with rapid, violent deposition. Among the fish are tiny glass spherules, tectites, some of them lodged in the gill arches of the buried fish as if they fell from the sky while the fish were still breathing. Fragments of amber, plant material, a pterosaur embryo, pieces of material consistent with impact ejecta embedded throughout. The interpretation of the Tanis site requires understanding the mechanism by which the energy of the Chicxulub impact, delivered 3,000 kilometers away in Mexico, could have reached North Dakota within hours and deposited this extraordinary assemblage. The mechanism is a siege, a resonant oscillation of a body of water triggered by the seismic waves from the impact. When the earthquake waves from Chicxulub reached the river system preserved at Tanis, they set the water in motion, not through a tsunami in the traditional sense, but through a rapid oscillation that repeatedly surged water inland and back, carrying fish and debris and depositing them in layers that preserved their contents with extraordinary fidelity. The tectites, the glass spherules formed from vaporized rock at the impact site, arrived later, raining down from the ejecta cloud that had been spreading around the planet. Their presence in the gill arches of the buried fish tells us that the fish were still alive and breathing when the tectites fell, that the seiches that killed and buried the fish occurred before the global tectite fallout, which took perhaps 15 to 20 minutes to reach North America from the impact site. This gives us a timeline of extraordinary precision. The fish were killed and buried by impact-generated seiches within minutes of the impact. The tectites arrived while the fish were still fresh within perhaps 15 to 20 minutes. The entire Tanis deposit was formed within the first day of the impact, possibly within the first few hours. The Tanis site is, in a very literal sense, a snapshot of a single day 66 million years ago. It is the most precisely dated event in the entire fossil record. A record of a specific morning preserved in such detail that we can read not just the season, but the approximate time of day from the biology of the organisms preserved there. What does Tanis tell us about the experience of the animals caught in the first hours? It tells us that the seismic waves arrived first, setting the rivers in violent motion before any other effect of the impact was visible. It tells us that the tectite rain, the falling glass spherules from the ejecta cloud, arrived within 15 to 30 minutes of the impact, a global rain of material from space reaching North America while the seismic chaos was still ongoing. And it tells us that whatever came next, whatever processes killed the animals that were not immediately buried in the siege deposits, happened quickly enough that there was no subsequent disturbance of the Tanis deposit before burial. In the context of the broader sequence of impact effects, this means that the animals at Tanis were caught in the first phase of a catastrophe that would unfold over hours, days, and months. They were killed by the most immediate effects, the seismic disruption, the seiche, possibly the first thermal pulse, before the global environmental effects had time to develop. They were, in a sense, the lucky ones. Not because their deaths were not terrible. Being buried in a violent surge of water is not an easy death. But because they died quickly in the first chaos of the event, before the slow and terrible days and weeks that followed. Day 0, the first hour, while the seismic waves were still traveling around the globe and the seiche deposits were being laid down at Tanis, The ejecta cloud was spreading above the atmosphere. The material ejected from the Chicxulub impact left the Earth at velocities exceeding escape velocity, moving fast enough to reach space before being pulled back by gravity. As this material spread through the upper atmosphere and beyond, and then began to fall back, it created a global ring of superheated particles descending toward the surface. The re-entry of ejecta particles into the atmosphere converted their kinetic energy to heat. In the upper atmosphere, this produced a global pulse of infrared radiation. Heat that radiated downward toward the surface. The intensity of this pulse, integrated over the entire sky, has been estimated to have been equivalent to several times the intensity of direct sunlight at noon. A global oven effect that lasted for perhaps 1 to several hours after the impact. The consequences of this thermal pulse for the surface of the Earth were severe. On exposed ground, open landscapes, the tops of forest canopies, any surface directly exposed to the sky, temperatures rose dramatically within the first hour. The precise temperature increase is a matter of ongoing scientific debate, with estimates ranging from a few degrees to hundreds of degrees depending on assumptions about ejecta density, atmospheric opacity, and other factors. What is less disputed is that the thermal pulse was sufficient to ignite wildfires in dry vegetation across large areas of the globe, and that any animal caught in the open without shelter from the radiant heat was in serious danger. The forests of Hell Creek in the final hour of their existence as intact ecosystems would have felt this heat. The drier vegetation, dead wood, dry grass, the leaf litter on the forest floor began to smolder and ignite. The fires started unevenly. Here, a fallen tree catching fire. There, a patch of dried ferns beginning to smoke. Within minutes, the fires spread, driven by the heat radiating from the sky and by the winds generated by the impact-triggered pressure waves that had been traveling through the atmosphere. The animals of the Hell Creek ecosystem responded to fire as animals have always responded to fire, by moving away from it. Herbivores stampeded away from the flames. Predators were driven by the same instinct, the ancient recognition of fire as threat overwhelming the behavioral patterns of the hunt. The river systems, as they always have, provided refuge. The wide, flat water offering protection from the advancing flames. The moist banks and floodplains providing somewhat cooler conditions than the burning uplands. But the rivers themselves were not safe. The seismic waves had disrupted their banks. The water levels were oscillating from the Sichi effects, and the sky above the rivers was still raining glass. The tektites falling from the ejecta cloud, tiny particles of impact glass that could be inhaled, that could damage respiratory tissue, that were the material evidence of a catastrophe whose scale no animal on Earth could have any framework for understanding. Day 0, hours 1 through 6. The wildfires that ignited in the first hour of the impact spread throughout the afternoon of impact day. The pattern of wildfire is recorded in the KPG boundary layer itself. Charcoal is found in the boundary clay. At sites around the world, the preserved residue of forests that burned on the day of the impact. The distribution of this charcoal is global, not everywhere, not with uniform intensity, but present across multiple continents and ocean basins, evidence of a worldwide fire event of unprecedented scale. The intensity and extent of the wildfires on impact day is one of the most debated aspects of the KPG event. Some researchers have argued for global firestorms, an essentially worldwide burning of surface vegetation driven by the thermal pulse from the ejecta reentry, while others have suggested that the wildfires were real, but more geographically limited, concentrated in the regions closest to the impact site and in areas where dry conditions made ignition easy. The charcoal evidence supports widespread, but not necessarily global fires. The North American record, closest to the Yucatan impact site and therefore most heavily affected by the thermal pulse, is particularly rich in impact day charcoal. Evidence from more distant sites, including Europe and Africa, also shows charcoal in the boundary layer, but the signal is variable and in some places ambiguous. What is clear is that the fires of impact day were not a brief localized event. They were a significant environmental disruption that lasted for hours and in some areas for days, consuming the dry vegetation of the late Cretaceous landscape and loading the atmosphere with smoke and particulates that would contribute to the longer-term environmental effects. For the animals of the Hell Creek ecosystem, the fires of the first day were a catastrophe in themselves, not necessarily lethal to all or even most individuals, since animals with access to rivers and wetlands had refuge, but disruptive in ways that would compound over the days that followed. The food supply of the large herbivores, the ferns and flowering plants and tree foliage that sustained the hadrosaurs and ceratopsians, was burning. The nest sites of birds and small dinosaurs were being destroyed. The cover that prey animals depended on was disappearing, and the fires were only the beginning. Day 0, the first night. By nightfall on Impact Day, if nightfall is even a meaningful concept when the sky is filled with smoke and ejected dust, the Hell Creek ecosystem was already profoundly disrupted. The fires were still burning in the uplands. The rivers ran dark with ash and disturbed sediment. The air carried the smell of smoke and something else, something acrid. The chemical signatures of the massive sulfur dioxide release from the vaporized target rock beginning to reach the lower atmosphere from the stratospheric heights where most of it had initially been injected. The large animals that had survived the first hours were in shock, not psychological shock, which requires a framework for understanding what has happened, but the biological shock of an organism whose environment has been suddenly and violently disrupted. They were cold. The thermal pulse that had heated the surface in the afternoon was over, and the smoke loading the atmosphere was already beginning to reduce the amount of sunlight reaching the surface. The temperature was falling faster than normal. The night was darker than normal. The dinosaurs that had spent millions of years in a world of reliable seasons, of predictable temperature rhythms, of stable vegetation communities, they were now in a world where none of those patterns held. The large triceratops that had been drinking from the river at dusk had no framework for understanding the darkness and the cold and the ash falling from a smoke-filled sky. It did not understand. It could not understand. It simply experienced. And what it experienced on this first night of the new world was discomfort and confusion and the absence of the familiar cues that had always structured its existence. Somewhere to the south, far to the south, beyond the range of any terrestrial animal's direct perception, the ground was still glowing. The Chicxulub crater, still hours after the impact, was a cauldron of molten rock and superheated gas, a wound in the Earth's surface so severe that it would not cool entirely for thousands of years. The energy still being radiated from the impact site warmed the atmosphere over the Gulf of Mexico and the Caribbean, driving convective storms of extraordinary violence, hurricane-force winds, torrential rain, conditions that would have been apocalyptic by any normal standard, but that were, in the context of what was already happening, simply one more element of a catastrophe with no name. Day 1, the morning after, the sun rose on a world already transformed. But the word rose is too simple. The sun was there, It had not changed, it had not moved. The solar energy reaching the top of the atmosphere was the same as it had always been. What had changed was the atmosphere itself. The ejecta cloud that had spread around the planet was beginning to settle, the larger particles falling out, the smaller ones lingering. The smoke from the wildfires was mixing with the stratospheric dust and the sulfur dioxide and sulfuric acid aerosols that were forming as the massive sulfur injection from the vaporized Yucatan anhydrite began to react with water vapor in the upper atmosphere. The sky on the morning of day 1 was not the clear blue sky of the late Cretaceous. It was brown, hazy. The sun, visible as a disk through the murk, was dimmer than it had been the day before. Visibly, measurably dimmer, not dramatically so, not yet. But the process that would eventually block out the sunlight almost entirely had begun. The animals that emerged from the night of impact day to face this morning were those that had survived the seismic disruption, the thermal pulse, the fires, and the darkness. What proportion of the Hell Creek fauna had made it through the first day is impossible to know with precision. The fossil record tells us about the before and the after, not about the moment-by-moment survival statistics of impact day. But we can reason about it. Large animals that had access to rivers and wetlands, the hadrosaurs and ceratopsians that frequented river margins, the crocodilians and turtles that spent most of their time in the water, the large T. Rex that had survived in part by virtue of having no predator that could threaten it had the best chance of surviving the first day. The fires did not reach the rivers. The seismic disruption, while violent, was not necessarily lethal for animals in open water. The thermal pulse, devastating to exposed vegetation, but partially buffered by water, would have been survivable for animals immersed or sheltered in wet environments. The smaller animals, birds and small mammals, and the various small dinosaurs and lizards that inhabited the forest floor faced a different calculus. Many of them depended on the forest for cover, for food, for nesting sites. The fires had destroyed much of this, but smallness is also an advantage in a crisis. Small animals need less food, can shelter in smaller spaces, can exploit microhabitats that are unavailable to large animals. The birds, in particular, had resources that the non-avian dinosaurs did not. The ability to fly, to cross rivers, to reach unburned areas, to find food in the canopy above the ash-covered ground gave the birds a mobility advantage that would prove critical in the weeks and months to come. Not all of them would survive, but some would. The mammals, small, mostly nocturnal, insectivorous and omnivorous, able to burrow and to tolerate a wide range of environmental conditions, had perhaps the best immediate prospects of any group. Their small size minimized their caloric requirements. Their generalist diets allowed them to exploit whatever food was available. Their burrowing behavior provided shelter from both the thermal pulse and the fires. In the terrible calculus of the first day of the New World, the mammals were, for once, in a relatively favorable position. Day 2, the cold begins. The second day after the impact was colder than the first. This is not what intuition might predict. The impact had released an enormous quantity of energy. Shouldn't the world have been heating up? In the immediate aftermath, yes. The thermal pulse of impact day had heated the surface, but the energy of the impact had also loaded the atmosphere with enormous quantities of dust, smoke, and sulfuric acid aerosols, and these were beginning to do what fine particles in the upper atmosphere always do: block sunlight. The sulfuric acid aerosols are particularly important here. The Yucatan target rock rich in anhydrite, calcium sulfate, had released an estimated 50 to 500 billion tons of sulfur dioxide when it was vaporized. This sulfur dioxide, injected high into the stratosphere by the violence of the impact, was reacting with water vapor to form sulfuric acid aerosols, tiny droplets of sulfuric acid suspended in the upper atmosphere. These aerosols are extremely effective at scattering and absorbing incoming solar radiation. The effect of a major volcanic eruption on global temperature gives us a useful analog. When Mount Pinatubo erupted in 1991, it injected approximately 20 million tons of sulfur dioxide into the stratosphere. Global temperatures dropped by approximately half a degree Celsius over the following year as the Pinatubo aerosols spread around the planet, reflecting a fraction of incoming sunlight back into space. The Chicxulub impact is estimated to have injected something in the range of 25 to 500 billion tons of sulfur dioxide, thousands to tens of thousands of times more than Pinatubo. The cooling effect was not half a degree, it was degrees, many degrees. Rapidly, over the course of days to weeks, the surface temperature of the Earth began to fall. On day 2, this cooling was just beginning, barely perceptible, not yet outside the range of normal day-to-day variation. The Triceratops moving across the ash-covered landscape of what had been the Hell Creek forest would not have registered it as anything distinctive. It was cool. The sky was strange, brown and hazy, the sun a pale disk rather than the bright presence it normally was. But the cold was within the range of what the animal had experienced on cool autumn mornings before. The vegetation was different. The fires had burned large areas of the upland forest. The surviving vegetation, the plants that had escaped the fires, that had been sheltered by topography or proximity to water, was covered in ash and blanketed by the continuing fall of fine ejecta particles. The broad leaves of the flowering plants were coated in gray. The ferns that carpeted the forest floor were matted and crushed. The air smelled of char and something acrid that none of the animals had experienced before, the sulfur chemistry beginning to work its way through the lower atmosphere. The large herbivores could still find food. The roots of plants survived underground. The watery stems of aquatic vegetation persisted in the rivers, and even the ash-covered vegetation possessed in the rivers, and even the ash-covered vegetation above ground. But the familiar abundance of the late Cretaceous forest was gone. The rich variety of food that had sustained the hadrosaur herds through millions of years of ordinary Cretaceous days had been dramatically reduced in a matter of hours. They were hungry, they were disoriented, they were alive. For now, day 3 through day 7, the temperature falls. The week following the impact was a week of progressive deterioration. Each day, the sky was slightly darker. Each day, the temperature was slightly lower. The changes were gradual enough that no individual organism would have registered them as obviously extraordinary. The decline was within the range of seasonal variation, at least in those first days, but it was consistent, directional. The downward trend did not pause or reverse. By the end of the first week, temperatures across much of the northern hemisphere had fallen by several degrees below the pre-impact baseline. Not catastrophically cold, not yet, but cold enough to stress the tropical and subtropical vegetation communities that had dominated the late Cretaceous landscape. Vegetation that was not adapted to cold temperatures, and that, already damaged by the fires and the ashfall, was struggling to maintain photosynthetic function in the reduced light of an atmosphere thick with aerosols. The food chain crisis that would eventually kill the large dinosaurs was already beginning at a microscopic level In the first week after the impact, photosynthesis was slowing. Not everywhere, not completely, but the rate at which plants were converting sunlight and carbon dioxide and water into organic matter was falling because the light available for photosynthesis was falling. The plankton in the ocean was beginning to experience the same reduction. The base of the food chain was weakening. The large herbivores did not feel this directly. Their food, plants, was still present, though damaged. The insects that depended on the plants were beginning to face the same stresses as the plants themselves. The small mammals and birds that depended on insects were finding food harder to locate. The cascade of effects was working its way up the food chain from the bottom, invisibly, in the first week after the impact. The T-Rex that had survived the fires was hungry. It had not made a successful hunt since before the impact. The prey herds were scattered and disrupted. The Edmontosaurus groups that normally moved in predictable patterns through familiar landscapes were now moving erratically through an ash-covered, fire-damaged world, their normal behavioral routines disrupted by the loss of the landmarks and vegetation structure they had navigated by for generations. Finding prey was harder. The normal ecological rhythms that a large predator depends on, knowing where the prey will be, at what time, in what kind of terrain, had been disrupted. But T-Rex had survived lean periods before. A large predator with a body built to sustain itself on irregular meals of enormous caloric content could go days or weeks without eating. The first week after the impact was terrible, but it was not yet beyond the physiological tolerance of a healthy adult T-Rex. The cold and the dark, however, were a different matter, and they were only just beginning. Week 2. The world goes dark. 2 weeks after the impact, the sky over the Hell Creek ecosystem was barely recognizable as a sky. The sulfuric acid aerosols had spread through the stratosphere with the efficiency of a global weather system, carried by the high-altitude winds that circumnavigate the Earth in days. The smoke from the wildfires, which had continued to burn in some regions for more than a week, had added its own load of fine particulates to the stratospheric haze. And the finest fraction of the impact ejecta, the microscopic dust that had been thrown highest into the stratosphere and that was slowest to settle, was still there, suspended above the aerosol layer, intercepting the sunlight before it could reach the lower atmosphere. Together, these 3 inputs to the stratospheric aerosol loading, sulfuric acid, soot, and impact dust, were reducing the amount of solar radiation reaching the surface of the Earth to a fraction of its normal value. Estimates of the reduction vary depending on which combination of aerosol loading models you use and which initial inputs you favor. But many of the most detailed studies suggest that by 2 weeks after the impact, the sunlight reaching the surface had been reduced to somewhere between 1% and 10% of its normal value. Not 1/10, between 1 and 10%. The compensation point of photosynthesis, the light level below which plants consume more energy through respiration than they produce through photosynthesis and therefore begin to die, is roughly 1% of full sunlight for most plants. At the light levels prevailing 2 weeks after the impact, the plants of the late Cretaceous were at or below their compensation point across large areas of the globe. The forests were not burning now, but they were dying. The process was not immediate or dramatic in appearance. A plant that cannot photosynthesize does not fall over and die in a day. It depletes its stored energy reserves, the sugars and starches it has accumulated, and it conserves, shutting down non-essential functions, closing its stomata to minimize water loss, pulling resources from the leaves and into the stems and roots. The leaves yellow, then they brown, then they fall. In the forests of the late Cretaceous, this process was happening on a global scale. Not uniformly. The reduction in sunlight varied by latitude and by local weather patterns, and some areas were less severely affected than others. But across the broad swath of temperate and subtropical North America, where the Hell Creek fauna lived, the forests were beginning the slow, visible process of dying. For the large herbivores, this was the beginning of the end. A triceratops weighing 8 tons requires an enormous daily caloric intake to sustain itself. In normal times, the late Cretaceous lowland forests provided this: a rich, diverse, continuously productive plant community that could sustain the largest herbivores in the history of terrestrial life. In the darkened, ash-covered, cold world of 2 weeks after the impact, the plants were failing. The leaves that remained were coated in ash and sulfuric acid deposits that made them less digestible and potentially toxic. The new growth that would normally have replaced eaten vegetation was not occurring. Plants were not producing new tissue without photosynthesis. The food supply was not simply reduced, it was failing. Edmontosaurus herds that normally ranged over dozens of square kilometers in search of food were now covering hundreds of kilometers, stripping whatever green material remained. Moving through a landscape of dead and dying vegetation in search of the patches where some fraction of normal productivity survived. The effort was greater, the food was less, and the calories burned in searching were calories that could not be replaced. The large herbivores were losing weight, not catastrophically, not yet. Their large bodies gave them significant reserves, but the trajectory was unmistakable. They were burning stored energy faster than they could replace it. The predators watched. T-Rex, in its own way, was facing the same crisis, not the immediate food crisis of the herbivores, but the secondary crisis of a predator whose prey is weakening and becoming easier to catch, but also becoming scarcer. The disrupted behavior of the prey herds made hunting simultaneously easier in some ways. Weakened animals are easier to catch and harder in others scattered. Erratic prey in unfamiliar terrain is harder to locate. And T-Rex was cold, not dangerously cold. Perhaps its large body mass buffered it against the falling temperatures, but cold in a way that it had never been before. The temperature in the Hell Creek region had fallen by the end of the second week to perhaps 10 or 15 degrees Celsius below the pre-impact baseline. This is not freezing cold. The late Cretaceous North America was warm, and even with a 10-degree drop, temperatures remained above freezing in most lowland areas. But for an animal adapted to a subtropical climate, the cold was metabolically significant. More energy was needed to maintain body temperature. More food was needed to provide that energy. Food that was becoming harder to find. Week 3, the ocean in crisis. The effects of the impact were not limited to the land. The ocean, which covers most of the Earth's surface and which is the foundation of the global biosphere in ways that the terrestrial world is not, was experiencing its own parallel catastrophe. The first effects on the ocean were physical. The impact had generated a tsunami of enormous scale, an ocean wave produced not by the wind or by a submarine earthquake, but by the direct displacement of water, by the asteroid impact, and by the collapse of the rim of the Chicxulub crater. The initial wave at the impact site was hundreds of meters tall, and as it spread outward across the shallow Caribbean Sea and into the open Atlantic and Pacific, it lost height but gained reach. Coastlines around the world were struck by waves that, while far smaller than the initial wave near the impact site,
were still of catastrophic height, tens of meters in many areas. The shorelines of the late Cretaceous world were different from those of today. The seaways that covered the continental interiors were in many places shallow and low-lying, making them particularly vulnerable to tsunami inundation. The coastal ecosystems, the shallow marine environments, where the food chain of the ocean begins, where the greatest biological productivity per square meter occurs, were physically disrupted by the tsunami within hours of the impact. But the tsunami, dramatic as it was not the most consequential impact on the ocean. That was the effect of the darkening of the atmosphere on photosynthesis. The base of the marine food chain is phytoplankton, microscopic, photosynthetic organisms that float in the sunlit surface layer of the ocean and that produce, through photosynthesis, the organic matter that sustains everything above them in the marine food web. They need light. Without adequate light, they cannot photosynthesis. Without photosynthesis, they die. The reduction in sunlight that was killing the terrestrial plants in the second and third weeks after the impact was doing the same thing to the phytoplankton of the ocean's surface. The phytoplankton blooms that had sustained the extraordinary productivity of the late Cretaceous ocean were collapsing. The microscopic grazers that fed on them, the zooplankton, the foraminifera, the tiny animals of the marine food web's base, were losing their food supply. The collapse of the phytoplankton did not immediately kill the large marine animals. Fish, mosasaurs, plesiosaurs, sea turtles, all of these animals had enough reserves and enough behavioral flexibility in their foraging to survive for weeks or months without the base of the food chain producing at its normal rate. But the crisis was propagating upward through the food web, slowly but inexorably, driven by the same basic principle that was driving the terrestrial crisis. Less energy at the base means less energy available at every level above. The chemistry of the ocean was also changing. The enormous quantities of carbon dioxide released by the vaporization of the Yucatan limestone, an estimated 1 trillion tons or more of CO2 in some estimates, were dissolving into the surface ocean and acidifying it. Ocean acidification is a process that directly affects organisms with calcium carbonate shells. The ammonites, the foraminifera, the vast community of shell-bearing invertebrates that populated the late Cretaceous ocean. Calcium carbonate dissolves in acidic conditions. The shells of these organisms were being chemically attacked from without at the same time that the base of the food chain was collapsing beneath them. The ammonites, one of the most abundant, most diverse, and most geologically long-lived groups of marine invertebrates present in the oceans for more than 300 million years, were facing simultaneous attack from two directions: starvation from above as the food web collapsed, and chemical dissolution from the acidification below. Not a single species of ammonite survived the KPG boundary. In the ocean, as on land, the end was coming. Not in days, not even in weeks for the largest animals, but in months, in a year. In the years that followed, the trajectory was set, and the trajectory pointed only one way. Month 1, the impact winter deepens. By 1 month after the impact, the global temperature had fallen dramatically. The precise magnitude of the cooling is debated. Models produce a range of estimates depending on assumptions about the initial aerosol loading and the optical properties of the various atmospheric contaminants. But a reduction of between 5 and 25 degrees Celsius in global mean surface temperature is within the range of most estimates. 5 to 25 degrees. In the context of the modern world, A 5-degree drop in global mean temperature would take the planet to Ice Age conditions. A 25-degree drop would be catastrophic beyond any historical analog. The KPG cooling falls within this range, and the actual magnitude, where within this range, is one of the genuinely uncertain parameters of the impact winter models. What is not uncertain is that the cooling was real, that it was global, and that it persisted for months to years. The sulfuric acid aerosols that drove the cooling are known to have a residence time in the stratosphere of 1 to 3 years. That is how long it takes for them to settle out or be washed out of the stratosphere by natural processes. During that entire period, they continued to reduce incoming solar radiation. The cooling was not a brief pulse, but an extended condition, a new and terrible climate that the biosphere had to endure for years. The plants of the Hell Creek ecosystem were, by 1 month after the impact, in catastrophic decline. The deciduous trees, the broad-leaved flowering plants that had dominated the late Cretaceous forest, had dropped their leaves, as they would in autumn. But it was not autumn. The signals driving leaf drop were the reduced light and the cold, the same signals that normally trigger autumn leaf drop being delivered in what should have been late spring or summer. The trees were not entering a normal dormancy. They were being pushed into a stress response, a desperate conserving of resources against conditions that had never existed in the evolutionary history of these plants. Some of the trees would survive. Not all. Many of the broadleaf species appear, from the paleontological record, to have gone locally or globally extinct in the immediate aftermath of the impact. The pollen record from KPG boundary sections shows a dramatic shift. The rich, diverse pollen assemblage of the late Cretaceous flora is replaced in the immediate boundary layer by a spike in fern spores. This fern spike, found in KPG sections around the world, records a phenomenon well known from the aftermath of modern environmental disasters. Ferns, which are stress-tolerant, rapidly colonize disturbed environments, appearing as the first plants to recolonize an area after a disturbance, before the slower-growing trees and flowering plants can re-establish themselves. The fern spike at the KPB boundary tells us that the forests of the late Cretaceous were not simply damaged, they were reset. The complex, multi-species forest communities that had taken millions of years to assemble were knocked back nearly or entirely to bare ground across large areas. The ferns colonized this ground rapidly. But ferns are not a forest. Ferns cannot support the food web that the late Cretaceous forest had sustained. The hadrosaurs did not eat ferns. The Triceratops did not eat ferns. The insects that pollinated the flowering plants could not survive on fern spores. The food web had not just been disrupted, it had been demolished. Month 2. The last herds. 6 weeks after the impact, the large herbivores of the Hell Creek ecosystem were dying. Not quickly, not dramatically. The way large animals die when their food supply fails. Slowly, incrementally, the energy balance tipping further negative each day. The body reserves that had sustained them through lean times being depleted faster than they could be replenished. The Triceratops, a few weeks after the impact, would have weighed less than it had before. Its ribs, normally not visible beneath the thick muscle and fat of a healthy animal, were becoming faintly visible beneath the skin. Its movements were slower, more deliberate, the unconscious conserving of energy that characterizes an animal in negative energy balance. It was still foraging, still searching, covering the degraded landscape in search of the green patches that survived, ripping up roots and tubers and the rhizomes of ferns when the above-ground vegetation was gone. The Triceratops' immune system was compromised by malnutrition. Its resistance to the parasites and pathogens that it normally carried at tolerable levels was weakening. The parasites were proliferating. Small injuries that would normally have healed quickly were slow to close. The animal was not simply hungry. It was sick. The social structure of the large herbivore groups, the herds, the family associations, the behavioral patterns that had organized Edmontosaurus into coherent groups moving together through a familiar landscape was breaking down. Animals were separating from groups as the energy cost of keeping up with the herd exceeded their capacity. The weak were falling behind. The strong were moving on. T. Rex was still alive. It had fed on the weakening prey. It had found the animals that had separated from their groups, that were moving slowly through unfamiliar terrain. The hunting had been easier than in normal times. In one sense, weakened, disoriented prey is easier to catch than healthy, alert prey in familiar territory. But T. Rex was also weakening. It had lost weight. The cold, the persistent, unnatural cold of the impact winter was taxing its thermoregulatory capacity, demanding more energy to maintain body temperature. The caloric balance was negative for T. Rex too, but T. Rex was still there. 6 weeks after the impact, T. Rex was still alive in the Hell Creek ecosystem, still hunting, still, in some functional sense, the apex predator of a world that was dying around it. The smaller animals were faring differently. The mammals, the small, burrowing, insectivorous mammals of the late Cretaceous, were struggling but surviving. Their burrows provided insulation against the cold. Their small size minimized their caloric requirements. The insects that formed their primary food supply were declining, but insects are remarkably resilient. Some species were surviving in the soil, in the bark of trees, in the microhabitats that the devastation of the surface world had not entirely destroyed. The mammals were hungry, but they were not yet dying. The birds were also surviving, after a fashion. Not all of them. The large flightless birds and the specialized birds most dependent on specific food sources were in trouble. But the small, generalist birds, the species capable of eating seeds, insects, berries, whatever was available, had a flexibility that was proving adaptive. They could fly to unburned areas. They could follow the rivers to find green patches of surviving vegetation. They could eat things that no dinosaur had ever eaten, accessing food resources that the specialized diets of the non-avian dinosaurs had never exploited. The crocodilians in the rivers were alive, cold-blooded, capable of going months without food, able to slow their metabolism to a fraction of its normal rate during periods of cold and food scarcity. The crocodilians were, in the context of the post-impact world, metabolically blessed. They retreated to the deeper pools of the rivers, their body temperatures falling with the water temperature, their metabolic rate slowing to near zero. They were not dead, they were waiting. The turtles were doing the same. The fish in the rivers, while stressed by the changed water chemistry and the disruption of their food supply, were surviving. The rivers continued to flow. The aquatic food chain was partially buffered from the worst effects of the atmospheric disruption, and the fish had the behavioral flexibility to exploit whatever food remained. The survivors of the KPG extinction were, in these early weeks, already distinguishing themselves by their survival strategies: small body size, metabolic flexibility, behavioral generalism, dietary breadth, These are the traits that were paying off in the post-impact world, and they are the traits that would define the survivors of the extinction, the ancestors of the modern world. The large, specialized, metabolically expensive, behaviorally rigid animals, the animals that had defined the Mesozoic world for tens of millions of years, were on a different trajectory. Month 3, silence spreading. By 3 months after the impact, the Hell Creek ecosystem was unrecognizable. The forest that had once covered the landscape was gone. Not entirely, not everywhere, but the complex, multi-layered canopy that had been the defining structural feature of the late Cretaceous lowland environment was reduced to bare trunks and fallen wood, interspersed with the first carpet of fern growth that was beginning to colonize the exposed ground. The flowering plants were not extinct. Their seeds survived in the soil. Their roots were still alive in many places, but the standing forest was gone. The temperature was, by this point, perhaps 10 to 15 degrees Celsius below the pre-impact baseline in the mid-latitudes. Water was freezing at night in areas that had never experienced frost in the entire Cretaceous period. Snow may have fallen in regions that had been subtropical only months before. The large dinosaurs that had survived the first 2 months were, by 3 months after the impact, dying in large numbers. The Triceratops herds that had still been moving through the landscape in month 2 were reduced to isolated individuals, animals weakened by months of malnutrition, moving slowly through a dead landscape. Their behavior becoming less coherent as starvation compromised their neurological function. T-Rex was dying too, not all at once, and not all individuals at the same rate. The largest individuals with the greatest body reserves would have lasted longest. But the prey that T-Rex needed was gone. The few surviving herbivores were widely scattered, their caloric content reduced by their own starvation. The energy cost of hunting them exceeded the energy obtained from catching them. T-Rex, the apex predator of the Mesozoic, was dying, not because anything had beaten it, but because the world that had sustained it no longer existed. It is worth sitting with that for a moment. T-Rex was not outcompeted. It was not killed by a superior predator. It was not driven to extinction by any failure of its own biology or behavior. It was killed by the collapse of its food web, by the loss of the plants that fed the animals that fed it, by the removal, in the space of 3 months, of the ecological foundation that had supported it and its kind for 2 million years. In the silence of the dying Hell Creek forest, on some afternoon in the 3rd month after the impact, the last T-Rex in that particular stretch of river valley moved slowly through the dead ferns, its head low, its eyes still scanning the landscape with the automatic alertness of a predator's nervous system, and found nothing. Nothing moved. Nothing smelled like prey. The landscape was silent in a way that it had never been in the entire history of the species. We do not know exactly when the last T-Rex died. The fossil record cannot give us that precision. What it can tell us is that above the KPG boundary, there are no T-Rex bones, not anywhere, in any formation, on any continent. The last T-Rex died in the months or years following the impact, and when it died, it left no descendants. The line in the rock marks its absence. Year 1. The survivors begin their inheritance. In the months after the impact, as the large non-avian dinosaurs were dying, something else was happening in the shadows of the dying forest. Something small and unremarkable and easy to overlook. Something that, in the long perspective of geological time, was perhaps the most significant biological development in the history of the planet. The survivors were eating. The small mammals that had burrowed through the impact winter were emerging from their refugia into a changed world. The world they found was degraded, cold, and largely stripped of the plant life that had structured it. But it was not empty. The seeds of the late Cretaceous flowering plants were still in the soil, buried dormant but viable. The ferns that had colonized the bare ground were producing spores. The insects that had survived in the soil and in the bark of dead trees were beginning to emerge. The rivers still flowed, carrying the organic debris of the devastated landscape to the sea, and the aquatic food chain was beginning slowly to recover. For a small mammal capable of eating seeds, insects, soft plant material, fungus, and virtually anything else organic, this degraded world was survivable. And surviving, in the context of a mass extinction, is everything. The earliest Paleogene mammals are known from fossil deposits that directly overlie the boundary clay in multiple locations around the world. These are small animals. Most of them weigh no more than a kilogram. Some are much smaller. They have generalist teeth. Not the highly specialized dentitions of the Cretaceous mammals evolved for specific dietary niches, but broader, more versatile tooth structures capable of processing a wider range of food. In the degraded landscape of the early Paleogene, this generalism was a competitive advantage of enormous magnitude. The ecological niche that the large dinosaurs had occupied were empty, completely empty. The competitive landscape had been reset, and the animals that survived were free, for the first time in the entire Mesozoic era, to diversify into those empty niches without the constraint of competition from the animals that had previously occupied them. The radiation of the mammals following the KPG extinction is one of the most dramatic evolutionary events in vertebrate history. Within 1 million years of the boundary, mammals had diversified into body sizes and ecological roles entirely inaccessible to them throughout the Mesozoic. Within 10 million years, the first large mammals had appeared, animals the size of tapirs, and then horses, and then rhinoceroses, filling the large herbivore niche left empty by the hadrosaurs and ceratopsians. Within 50 million years, the first whales had taken to the sea. Within 65 million years, the mammals had produced animals of greater size, range, greater ecological diversity, and in at least one lineage, greater cognitive complexity than anything the Mesozoic had contained. But in year one after the impact, the mammals were not radiating into ecological dominance. They were surviving day by day in a world still profoundly disrupted. The birds that survived the impact were in a similar ecological position to the surviving mammals. They were small, they were generalists, and they were benefiting from the emptying of the ecological landscape that the extinction of the large dinosaurs represented. But the bird story has a fascinating additional layer. The extinction was selective, and the pattern of survival tells us something important about which characteristics were most adaptive in the post-impact world. The late Cretaceous was already rich in avian diversity by the time of the impact. Among the most successful groups were the Enantiornithes, a major clade of Cretaceous birds that had diversified extensively throughout the period. They had claws on their wings. Many were specialized for life in trees. The Enantiornithes did not survive the KPG extinction. Not a single species of Enantiornithine bird survived to the Paleogene. The entire group was completely eliminated. The birds that survived were the Nornithines, the group that includes all living birds today. Within the Neornithines, the pattern of survival appears to have been connected to ecology. The species that survived were predominantly ground-dwelling or water-associated birds with seed-eating or generalist dietary capabilities.
birds that did not depend on the living forest for their food or their habitat. The arboreal specialists, the insectivores dependent on specific insect prey, the birds of prey that needed large vertebrate prey. These groups were disproportionately lost. The reason the Enantiornithes went extinct while the Nenornithines survived is not fully understood. The differences in ecology and life history between the two groups are real but subtle, and the pattern of extinction is not perfectly explained by any single characteristic. But the broad pattern is consistent with what would be predicted from the nature of the post-impact environment in which the living forest had been largely destroyed, and the food resources most reliably available were seeds, soil, organisms, and aquatic prey. The crow, the duck, and the chicken are the evolutionary heirs of the survivors. The Enantiornithes are gone. Their millions of years of evolutionary history ended at the KPG boundary as completely as the non-avian dinosaurs that were their distant cousins. The ocean recovery was, in many ways, the most dramatically documented of the post-impact ecological recoveries, because the marine sediment record preserves it in extraordinary detail. The extinction of the marine plankton at the KPG boundary is one of the most precisely documented events in the paleontological record. In KPG boundary sections, from the deep ocean floor, the change is abrupt and total. Rich, diverse assemblages of late Cretaceous plankton are replaced, literally at the boundary clay, by assemblages of a single surviving species, or a very few, the survivors of a mass extinction that eliminated the great majority of planktonic species that had existed in the Cretaceous ocean. Above the boundary, the recovery begins. Slowly at first, then over tens of thousands of years, new species appear, not survivors of the extinction, but genuinely new species evolved from the survivors in the altered conditions of the early Paleogene ocean. The diversity grows. The ecological complexity of the plankton community increases. The base of the marine food chain rebuilds. This recovery took a long time. Studies of deep-sea sediment cores show that the marine ecosystem did not return to anything like its pre-extinction complexity for several million years after the KPG boundary. The late Cretaceous ocean, with its extraordinary diversity of ammonites, mosasaurs, plesiosaurs, and the complex plankton communities that sustain them, was not simply disrupted and rebuilt. It was fundamentally transformed. The Paleogene ocean that replaced it was organized differently, dominated by different groups with a different food web structure that reflected the selective losses of the extinction. The ammonites, 340 million years of evolutionary history, were gone. Their ecological roles were eventually filled by other mollusks, but the ammonites themselves were finished. The mosasaurs and plesiosaurs were gone. Their large predator roles were eventually filled, millions of years later, by the evolving whales. The diversity of large marine reptiles that had characterized the Mesozoic ocean would not be seen again. What replaced them was different, not worse necessarily, not less ecologically complex, but irreversibly different because extinction is irreversible. The specific evolutionary lineages that were lost at the KPG boundary will not return. Year 2 through year 10, the slow recovery on land. The impact winter lasted based on climate model simulations and on evidence from the geological record for somewhere between 1 and several years. As the sulfuric acid aerosols settled out of the stratosphere, and as the atmospheric soot was washed out by precipitation, the light levels
slowly recovered. The temperature, after falling to its minimum sometime in the first year, began to recover slowly, unevenly, with setbacks, but directionally upward. As the light recovered, the plants began to recover with it. The ferns that had colonized the bare ground were joined by the first regrowth of flowering plants from the seeds and roots that had survived in the soil. The forest did not simply regrow. New species combinations formed as the survivors recolonized the landscape in the order and proportion determined by their specific ecological characteristics, their seed dispersal mechanisms, their growth rates, their tolerance of the altered soil chemistry. The forest that formed in the early Paleogene was not the late Cretaceous forest restored. It was a new forest, simpler in structure, lower in diversity, organized around the survivors rather than the former community. For the surviving mammals, the recovery of the plant community was opportunity. As the vegetation reestablished, the resources available to the small seed-eaters and omnivores increased. The mammals began to diversify. Within a few 100,000 years of the KPPG boundary, the first mammals larger than a rabbit had appeared in North America. Within 1,000,000 years, animals the size of sheep were present. The body size distribution of the mammals was expanding upward, filling the ecological space left empty by the extinct large herbivores. The early Paleogene was a period of ecological instability, a world in the process of reorganizing itself, with the rules still being established, the dominant groups not yet determined, the outcomes still genuinely open. The archaic mammals of the earliest Paleogene, the condylarths and the multituberculates, and the various other groups that diversified in the immediate aftermath of the extinction, were not the ancestors of the modern mammals in most cases. Many of them went extinct in their turn, replaced by the modern mammalian orders that emerged later in the Paleogene. The story of the recovery is a story of multiple false starts, of diversifications that did not persist, of ecological experiments that failed and were replaced by new ones. Evolution is not teleological. It does not aim at a specific outcome. The mammals that eventually dominated the Paleogene were not predetermined successors to the dinosaurs. They were the survivors of a series of ecological tests, each one selecting for characteristics that worked in the specific conditions of the specific moment. Could it have gone differently? This is a question about contingency, about the role of chance in the history of life. And the answer is yes, it could have gone very differently. The Chicxulub impact was not inevitable. The asteroid had orbited the Sun for billions of years in relative stability. Small gravitational perturbations had gradually shifted its orbit until it intersected the Earth's. A slightly different perturbation at a slightly different time would have shifted the orbit slightly differently, and the asteroid would have missed. If the asteroid had missed, the world would be different today, very different. The late Cretaceous was not a world on its way to extinction by any ordinary measure. The dinosaurs were not in decline. T-Rex was not a fading dynasty. It was a thriving species at the peak of its ecological success. There is no reason from the evidence to think that the non-avian dinosaurs were doomed without the impact. In a world without the Chicxulub impact, the dinosaurs would almost certainly still be here. In some form, the world's 66 million years from the late Cretaceous would not look like the late Cretaceous because evolution does not stand still. But the lineage would have continued. The dinosaur dynasty, which had already lasted 160 million years at the time of the impact, might have lasted another 100 million or more. And in that world, the mammals would not have diversified. They would have continued as they had for the entire Mesozoic, small and nocturnal and ecologically constrained by the competitive dominance of the large dinosaurs. The primates would not have existed, or would have existed as small tree-dwelling insectivores with no prospect of the cognitive expansion that post-Cretaceous conditions ultimately made possible. There would be no human beings in a world without the Chicxulub impact. This is not speculation. It is the logical consequence of what we know about the ecological dynamics of the Mesozoic and the conditions required for mammalian diversification. We exist because of the impact. Our existence is contingent on a catastrophe, on the death of the dinosaurs, on the suffering of the creatures that lived through the impact winter, on the extinction of 3/4 of all species on Earth. This is an uncomfortable thought. It is also the truth. The Deccan traps, a contributing factor. The Chicxulub impact was not the only geological upheaval at the end of the Cretaceous. In what is now India, an enormous volcanic event had been underway for perhaps 1 million years before the impact and continued for perhaps 1 million years afterward. The Deccan traps erupted approximately 1 million cubic kilometers of basaltic lava, releasing enormous quantities of carbon dioxide, sulfur dioxide, and water vapor that contributed to late Cretaceous climate instability. Some researchers have argued that the Deccan volcanism, acting over hundreds of thousands of years, had already stressed the late Cretaceous ecosystems and made them more vulnerable to the impact. Others have found that the eruptions were of insufficient intensity at any given point to have caused significant extinctions by themselves. The relationship between the Deccan eruptions and the KPG extinction has been further complicated by evidence that the impact may have intensified the Deccan volcanism. Studies suggest that the enormous seismic waves generated by the Chicxulub impact traveling through the body of the Earth may have triggered a pulse of increased volcanic activity in the Deccan province approximately 30 minutes after the impact, squeezing magma chambers and releasing additional eruptions. If true, the two great geological events of the KPG boundary were not independent. The impact triggered more volcanism, which added to the atmospheric loading of gases and aerosols, which extended and potentially intensified the environmental consequences. The catastrophe compounded itself. The current scientific consensus places the asteroid impact as the primary driver of the KPG mass extinction. The Deccan volcanism is seen as a contributing stress, a background factor that may have made the ecosystems less resilient, but that was not, by itself, capable of causing the extinction we observe. The debate continues, and new evidence from more precisely dated volcanic deposits continues to refine our understanding. What is not debated is that the world at the end of the Cretaceous was under stress from multiple directions, and that the coincidence of all these stresses produced a catastrophe of exceptional severity. The line in the rock marks the convergence of all of it, the 5 great extinctions. The KPG extinction was not the only mass extinction in Earth's history. It was not even the largest. The Permian-Triassic extinction, approximately 252 million years ago, eliminated an estimated 96% of all marine species and 70% of all terrestrial vertebrate species. It was more severe by any measure of proportional biodiversity loss than the KPG event. Its causes are still debated, but the evidence strongly implicates the massive Siberian traps volcanic eruptions, which released enough carbon dioxide and methane to trigger severe global warming, ocean acidification, and ocean deoxygenation over a period of perhaps 100,000 years. The Ordovician Silurian extinction approximately 445 million years ago, was the second largest in the fossil record, eliminating perhaps 85% of all marine species. The late Devonian extinction, approximately 375 million years ago, eliminated perhaps 75% of all species over a period of several million years. The Triassic-Jurassic extinction, approximately 201 million years ago, eliminated approximately half of all known species and cleared the ecological stage for the diversification of the dinosaurs that followed. These events are part of the background of geological time, the recurring pattern of catastrophic disruption and recovery that has shaped the history of life on Earth from its earliest chapters. Mass extinctions are not anomalies in the history of life. They are features of it, recurring intervals of elevated extinction rate that have repeatedly reshaped the living world and opened evolutionary space for the diversification of surviving lineages. The history of life is not a smooth progression toward greater complexity or greater diversity. It is a jagged, discontinuous process of accumulation and collapse, of extinction and radiation, of the building of complexity over millions of years and its destruction in geological instance. The Mesozoic world, built over 180 million years, was dismantled in months. The Paleogene world that replaced it took tens of millions of years to achieve comparable complexity. And yet, life persists. Through the Permian extinction, through the Ordovician extinction, through the KPG event, through the catastrophe the Earth has visited upon its biosphere, some lineages have survived and continued. Not the same lineages, not the same specific species, but life, continuing and diversifying and occupying the ecological space that opens in the aftermath of each event. This persistence is perhaps the most important fact about life on Earth. Not any specific adaptation, not any particular species, not any individual catastrophe or recovery. The persistence, the relentless, creative, improbable continuation of the biological experiment across 4 billion years and every catastrophe the solar system has thrown at it. We are part of that experiment. End of Part 4, approximately 22,000 characters. Continuing in Part 5, Asteroid Detection and Planetary Defense. The KPB, Boundary as a Place You Can Visit, a meditation on deep time, the line in the rock, and what it means that we exist. The birds that survived the impact were in a similar ecological position to the surviving mammals. They were small, they were generalists, and they were benefiting from the emptying of the ecological landscape that the extinction of the large dinosaurs represented. But the bird story has a fascinating additional layer because the extinction was selective in ways that reveal something important about which ecological characteristics were adaptive in the post-impact world. The late Cretaceous was already rich in avian diversity by the time of the impact. Birds had diversified substantially during the Cretaceous, and the fauna of the Hell Creek Formation included numerous species representing multiple lineages. Among the most successful of these groups were the Enantiornithes, a major clade of Cretaceous birds that had diversified extensively throughout the period. They had claws on their wings. Many were specialized for life in trees. They occupied the arboreal niches of the Cretaceous forest canopy in the way that many modern songbirds occupy these niches today. The Enantiornithes did not survive the KPG extinction. Not a single species of Enantiornithine bird survived into the Paleogene. The entire group, one of the most successful avian eliminators of the Mesozoic, was completely eliminated. The birds that survived were the Neornithines, the group that includes all living birds today. Within the Neornithines, the pattern of survival appears to have been closely connected to ecology. The species that crossed the KPG boundary were predominantly ground-dwelling or water-associated birds with seed-eating or generalist dietary capabilities. Birds that did not depend on the living forest canopy for their food or their habitat. The arboreal specialists, the dietary specialists, the birds of prey that needed large vertebrate animals, these groups were disproportionately lost. A 2018 study by Daniel Field and colleagues published in Current Biology concluded that the collapse of the global forest was the key filter in the avian extinction. The forest fell. The birds that needed the forest fell with it. The birds that could live on bare ground, in open water, along river margins, in the low fern-covered landscape of the early Paleogene survived. The crow, the duck, and the chicken are the evolutionary heirs of those survivors. The enantiornithes, after tens of millions of years of success, are gone. Their evolutionary history ended at the KPG boundary as completely as the non-avian dinosaurs that were their distant cousins. This is a reminder worth dwelling on. Evolution does not reward excellence in any absolute sense. It rewards fit in the precise biological meaning of that word, the match between an organism's characteristics and the specific conditions of the specific moment. The enantiorniths were excellently fitted to the late Cretaceous world. They were poorly fitted to the post-impact world. The neornithines were moderately fitted to the late Cretaceous world, living in the ecological margins. They were well fitted to the post-impact world, and so the world belongs to them. The ocean recovery was, in many ways, the most precisely documented of the post-impact ecological recoveries, because the marine sediment record preserves it in extraordinary resolution and continuity. The extinction of the marine plankton at the KPG boundary is one of the most thoroughly documented events in the entire paleontological record. In KPG boundary sections from the deep ocean floor, the change is abrupt and total. Rich, diverse assemblages of late Cretaceous plankton are replaced, literally at the boundary clay, by assemblages of a single surviving species or a very few. Above the boundary, the recovery begins, slowly and over tens of thousands of years, as new species evolve from the survivors in the altered conditions of the early Paleogene ocean. This recovery took a long time. Studies of deep-sea sediment cores show that the marine ecosystem did not return to anything like its pre-extinction complexity for several million years after the KPB. In some regions and for some groups, full recovery of diversity took 10 million years. Or more, the Ammonites' 340 million years of evolutionary history were gone. Not a single species survived the KPG boundary. Their ecological roles were eventually filled by other mollusks, but the Ammonites themselves were finished. The mosasaurs and plesiosaurs were gone. Their large predator roles in the marine ecosystem were eventually filled millions of years later by the evolving whales. The diversity of large marine reptiles that had characterized the Mesozoic ocean would not be seen again. What replaced them was different, not worse necessarily, but irreversibly different, because extinction is irreversible. The specific evolutionary lineages lost at the KPG boundary will not return. Every species that goes extinct takes with it not just itself, but all the species it could have become over millions of years of future evolution it will never experience. Year 2 through year 10, the slow recovery on land, the impact winter lasted based on climate model simulations and on evidence from the geological record for somewhere between 1 and several years. As the sulfuric acid aerosols gradually settled out of the stratosphere, and as the atmospheric soot was washed out by precipitation, the light levels slowly recovered. The temperature, after falling to its minimum sometime in the first year, began to climb again, slowly, unevenly, but directionally upward. As the light recovered, the plants recovered with it. The forest did not simply regrow. New species combinations formed as the survivors recolonized the landscape in the order and proportion determined by their specific ecological characteristics. The forest that formed in the early Paleogene was not the late Cretaceous forest restored. It was a new forest, simpler in structure, lower in diversity, organized around the survivors rather than the former community. For the surviving mammals, the recovery of the plant community was an enormous opportunity. The mammals began to diversify. Within a few 100,000 years of the KPG boundary, the first mammals larger than a rabbit had appeared in North America. Within 1,000,000 years, animals the size of sheep were present. The body size distribution of the mammals was expanding upward, filling the ecological space left empty by the extinct large herbivores, the archaic mammals of the earliest Paleon. The condylarths and the multituberculates and the various other groups that diversified immediately after the extinction were not the ancestors of the modern mammals in most cases. Many of them went extinct in their turn, replaced by the modern mammalian orders that emerged later in the Paleogene. The story of the recovery is a story of multiple false starts, of ecological experiments that failed and were replaced by new ones. Evolution is not teleological. The mammals that eventually dominated the Paleogene were not predetermined successors to the dinosaurs. They were the survivors of a series of ecological tests, each one selecting for characteristics that worked in the conditions of that specific moment, each one building on what the previous round had left behind. This process, running forward from the KPG boundary, produced the modern world of mammals. It produced the horse and the elephant, and the bat and the whale, and the primate. It produced, through the primate lineage, the great apes and the hominins, and eventually, 300,000 years ago, our own species. A species that can look back across 66 million years of evolutionary history and ask what happened on that morning in the late Cretaceous. And that has developed the tools to partially answer the question. Could it have gone differently? The Chicxulub impact was not inevitable. The asteroid had orbited the Sun for billions of years in relative stability. Small gravitational perturbations had gradually shifted its orbit until it intersected the Earth's. A slightly different perturbation at a slightly different time would have shifted the orbit slightly differently, and the asteroid would have missed. If the asteroid had missed, the world would be profoundly different today. The late Cretaceous was not a world on its way to extinction by any ordinary measure. The dinosaurs were not in decline. T-Rex was not a fading dynasty. It was a thriving species at the peak of its ecological success. There is no evidence from the fossil record to suggest that the non-avian dinosaurs were headed for extinction without the impact. In a world without the Chicxulub impact, the dinosaurs would almost certainly still be here. The dinosaur dynasty, which had already lasted 160 million years at the time of the impact, might have lasted another 100 million or more. And in that world, the mammals would not have diversified into ecological dominance. They would have continued as they had for the entire Mesozoic, small and largely nocturnal, and ecologically constrained by the competitive dominance of the large dinosaurs. The primates would not have existed or would have existed as small tree-dwelling insectivores with no prospect of the cognitive expansion that post-Cretaceous conditions ultimately made possible. There would be no human beings in a world without the Chicxulub impact. This is not speculation. It is the logical consequence of what we know about the ecological dynamics of the Mesozoic and the conditions required for mammalian diversification. We exist because of the impact. Our existence is contingent on a catastrophe, on the death of the dinosaurs, on the suffering of the creatures that lived through the impact winter, on the extinction of 3/4 of all species on Earth. This is an uncomfortable thought. It is also the truth. The Deccan traps, a contributing factor. The Chicxulub impact was not the only geological upheaval at the end of the Cretaceous. In what is now India, an enormous volcanic event had been underway for perhaps 1,000,000 years before the impact and continued for perhaps 1,000,000 years afterward. The Deccan traps erupted approximately 1,000,000 cubic kilometers of basaltic lava, releasing enormous quantities of CO2, sulfur dioxide, and water vapor that contributed to late Cretaceous climate instability. The relationship between the Deccan eruptions and the KPG extinction has been further complicated by evidence that the impact itself may have intensified the Deccan volcanism. A 2015 study by Mark Richards and colleagues proposed that the enormous seismic waves generated by the Chicxulub impact may have triggered a pulse of increased volcanic activity in the Deccan province. Approximately 30 minutes after the impact, squeezing magma chambers and releasing additional eruptions. If this interpretation is correct, the two great geological events of the KP boundary were not independent. The impact triggered more volcanism, which added to the atmospheric loading, which extended and intensified the consequences. The catastrophe compounded itself. The current scientific consensus places the asteroid impact as the primary driver of the KPG mass extinction. The Deccan volcanism is a contributing stress. What is not debated is that the world at the end of the Cretaceous was under stress from multiple directions simultaneously, and that the convergence produced a catastrophe of exceptional severity. The line in the rock marks the convergence of all of it. The 5 great extinctions. The KPG extinction was not the only mass extinction in Earth's history. It was not even the largest. The Permian-Triassic extinction, approximately 252 million years ago, eliminated an estimated 96% of all marine species and 70% of all terrestrial vertebrate species. It was more severe than the KPG event by any measure of proportional biodiversity loss. Its causes strongly implicate the massive Siberian Traps volcanic eruptions, which released enough carbon dioxide and methane to trigger severe global warming, ocean acidification, and ocean deoxygenation. This event came close to ending complex, multicellular life on Earth entirely. The Ordovician Silurian extinction, approximately 445 million years ago, was the second largest in the fossil record, eliminating perhaps 85% of all marine species. The late Devonian extinction, approximately 375 million years ago, eliminated perhaps 75% of all species over a period of several million years. The Triassic-Jurassic extinction, approximately 201 million years ago, eliminated approximately half of all known species and cleared the ecological stage for the great radiation of the dinosaurs that followed. These 5 events are the major mass extinctions of the Phanerozoic, the half-billion-year period of complex animal life. They are part of the background of geological time the recurring pattern of catastrophic disruption and recovery that has shaped the history of life on Earth. Mass extinctions are not anomalies. They are features of the history of life. Recurring intervals of elevated extinction rate that have repeatedly reshaped the living world and opened evolutionary space for the diversification of surviving lineages. The history of life is not a smooth progression toward greater complexity or greater diversity. It is a jagged, discontinuous process of accumulation and collapse, of extinction and radiation, of the building of complexity over millions of years and its destruction in geological instants. The Mesozoic world, built over 180 million years, was dismantled in months. The Paleogene world that replaced it took tens of millions of years to achieve comparable complexity, and yet life persists. Through the Permian extinction that nearly ended it, through the KPG event, through every catastrophe the Earth has visited upon its biosphere, some lineages have survived and continued. Not the same lineages, not the same specific species, but life, continuing and diversifying and occupying the ecological space that opens in the aftermath of each catastrophe. This persistence is perhaps the most important fact about life on Earth. Not any specific adaptation, not any particular species, not any individual catastrophe or recovery. The persistence, the relentless, creative, improbable continuation of the biological experiment across 4 billion years, and every challenge the solar system and the Earth's own geology have placed before it. We are part of that experiment, one chapter in a story far longer and far stranger than any human history, connected by the unbroken thread of biological inheritance to every living thing on this planet. The line in the rock marks one chapter's end and another chapter's beginning. The line in the rock is real. You can go and see it. In the cliffs of Stevens Klint in Denmark, a UNESCO World Heritage Site, since 2014, the boundary layer is exposed in the face of white chalk cliffs above the Baltic Sea. The chalk below it is gray-white and clean, full of the fossil remains of late Cretaceous marine organisms. The boundary layer itself is dark, a few centimeters of gray-black clay, visibly distinct from the chalk above and below. Above it, the chalk is different in color and texture, impoverished in fossils, the record of a sea recovering from catastrophe. You can put your hand on the chalk below the boundary and rest your fingers on the rock of the Cretaceous world. You can move your hand a few centimeters upward and cross the boundary. You can touch the rock of the world that came after. The geological scale of that movement, a few centimeters of rock representing roughly 100,000 years of accumulated sediment, is difficult to hold in the mind. But the physical experience of the transition is real. Below, one world. Above, another. The line itself, a catastrophe. The Stevens Klint site is beautiful. The sea below the cliffs is cold and gray and northern. Seabirds call above the white chalk faces. The wind off the Baltic carries the smell of salt and distance. And the line in the rock, 66 million years old, holds its quiet record of what happened. This is what geology does. It makes the past physical. It gives you a place to stand, a surface to touch, a tangible connection to events of a scale and remoteness that would otherwise be purely abstract. The KPG boundary is not an idea. It is a thing. It exists in space, in rock, on multiple continents, accessible to anyone who chooses to seek it out. And what it records is not simply a catastrophe. It records a transition, the most consequential transition in the history of vertebrate life on Earth. The transition from a world organized around one group of animals to a world organized around another. The transition from the age of dinosaurs to the age of mammals, the transition that, after 65 million years, produced the species thinking about it tonight. You can see the KPG boundary in other places too. In the Raton Basin, on the border of New Mexico and Colorado, highway road cuts expose the boundary in the coal-bearing sediments of a late Cretaceous swamp environment, and you can stop at the side of the road and find the thin, dark layer yourself. In the limestone of Spain and Italy, in the chalk of the Netherlands, not far from the original site where Mosasaurus hoffmanii was pulled from the ground in the 18th century, in the shale of New Zealand, in the sediment of Japan, in the rock of Antarctica. The line is everywhere. It ran around the whole planet 66 million years ago, and the planet has preserved it. It is patient in the way that rock is patient. It does not demand to be found. It simply waits in the dark below the surface, or exposed in a cliff face or a road cut, until someone with the knowledge to recognize it comes along. And when they do, and when they look at it carefully, the line tells its story with a directness that no textbook can quite match. Something ended here. Something began here. And the beginning is still ongoing. The question that the KPG boundary inevitably raises for anyone who sits with it long enough is, can it happen again? The answer, in principle, is yes. It can happen again. The solar system still contains objects of sufficient size to cause a mass extinction if they were to strike the Earth. The probability of an impact by an object of Chicxulub scale in any given year is extremely small. Astronomers estimate it at roughly 1 chance in several hundred million per year. But the solar system is old and the future is long, and a small annual probability accumulates into a meaningful likelihood over millions and billions of years. The difference between the late Cretaceous and today is that we know the threat exists. The dinosaurs did not. There was no cognitive capacity, no technology, no organized awareness of the solar system and its contents that could have detected the approaching asteroid and done anything about it. The asteroid approached from space, from outside the atmosphere, on a trajectory that no ground-level organism could detect until the final seconds. There was no warning. There could not have been. We have that capacity now. In the decades since the discovery of the Chicxulub crater and the establishment of the asteroid impact theory, humanity has developed increasingly sophisticated programs for detecting near-Earth objects. The NASA Center for Near-Earth Object Studies, based at the Jet Propulsion Laboratory in California, tracks thousands of known near-Earth asteroids, monitoring their orbits and projecting their future trajectories with precision that improves every year. The European Space Agency has equivalent programs. The Catalina Sky Survey, the Pan-STARRS Telescope Network, and other survey programs scan the sky systematically, cataloging every near-Earth object they can detect. These tracking networks have now identified the vast majority of the kilometer-scale objects in near-Earth orbits, and none of them pose a known threat in the foreseeable future. The large impactor problem for the next century or two is essentially solved at the level of detection. We know where the large asteroids are. We can say, with a high degree of confidence, that none of the known large near-Earth asteroids will strike the Earth in the next century. The more difficult problem is smaller objects too faint to detect at great distances that could still cause regional or continental scale devastation without the global mass extinction effects of a Chicxulub scale impactor. Objects tens to hundreds of meters in diameter fall into this category. Their number is vast. Their discovery rate is still incomplete. and the warning time for an undetected object of this size could be very short. The Chelyabinsk meteor of 2013, which was only about 20 meters in diameter, arrived entirely without warning and injured over 1,000 people in Russia through the shockwave from its atmospheric explosion. A 100-meter object would be far more destructive, but the most important development in planetary defense in recent years was not a detection program. It was a demonstration that detection alone is not enough. In September 2022, NASA's DART spacecraft, the Double Asteroid Redirection Test, deliberately impacted the small asteroid Dimorphos, a moon of the larger asteroid Didymos, and successfully altered its orbital period by approximately 33 minutes. This was not a defense against an imminent threat. It was a proof of concept, a demonstration that the technology for planetary defense is not purely theoretical. A spacecraft launched with sufficient lead time can change the trajectory of an asteroid through the kinetic energy of a deliberate collision. The dinosaurs had no warning and no defense. The asteroid approached and it struck, and the world ended in a matter of months. We have warning, we have in principle defense. Whether we invest adequately in both, whether we take seriously the lesson that the KPG boundary teaches about the vulnerability of even the most successful species on a planet with an active solar system, is a question that the line in the rock leaves open. It is a question worth answering carefully because the line exists and the solar system has not changed. The last days of the dinosaurs are also, in a very real sense, the first days of our world. Consider the timeline carefully. The KPG extinction occurred approximately 66 million years ago. The first primates appeared approximately 65 million years ago. Within 1 million years of the extinction, in the diversification of the surviving mammals into the empty ecological niche of the early Paleogene forest, the genus Homo appeared approximately 2 to 3 million years ago. Homo sapiens appeared approximately 300,000 years ago. Human civilization, in the sense of organized agriculture and settled communities, appeared approximately 12,000 years ago. On the geological timescale, the interval between the KPG extinction and the appearance of human civilization is not long. 66 million years is, by the standards of the history of life, a relatively short time. We are close in geological terms to the catastrophe that produced us. The gap between the last non-avian dinosaur and the first stone tools is smaller in proportion to the age of the Earth than the gap between any two people sitting in the same room. This proximity is not visible in our daily experience. We have no felt sense of the 66 million years of evolution that stand between us and the KPB boundary. The dinosaurs seem remote, almost mythological, their existence the subject of books and museums and children's toys rather than felt personal history. The small Paleogene mammals that were our remote ancestors seem, if anything, even more remote, less glamorous, less present to the imagination than the great animals they replaced. And yet the connection is there, biological, genealogical, real in the most concrete sense. Every mammal on Earth, including every human being, carries in its genome the evolutionary history of the post-Cretaceous radiation, the genes that govern the basic architecture of mammalian biology. The four-chambered heart, the insulating hair, the complex brain, the live birth and prolonged parental care, the warm metabolism. These are features that were present in the small mammalian survivors of the KPG extinction and that have been inherited with modification by every mammal that has lived since. We are the descendants of the survivors, not in a metaphorical sense.
in the literal, biological, genealogical sense. Every human being alive today is connected by an unbroken chain of reproductive events spanning 66 million years to the small, burrowing, insectivorous mammals that survived the impact winter, to the animals that crawled through the ash-covered ground of the early Paleogene, eating whatever they could find, surviving day by day in the ruins of the Mesozoic world. The burrowing behavior that saved them is still present in modified form in the way we seek shelter. The nocturnal habits that allowed them to avoid predators are still reflected in our visual system, our color vision, our sensitivity to certain kinds of light. The social behaviors that allowed some mammalian lineages to benefit from group living are the deep roots of human sociality. We carry these ancient adaptations layered under 66 million years of evolution in our biology. This connection is not visible. It is not felt in daily life, but it is real, and knowing it changes something about how the KPG boundary feels when you stand in front of it. There is a particular quality of feeling that comes from genuinely absorbing this history. Not the abstract knowledge that the dinosaurs existed and went extinct, which most people acquire in childhood and file away with other facts. Not the intellectual appreciation of the geological evidence, which is the property of specialists. Something more personal, more unsettling, more alive. The feeling of understanding that the world as we know it, with all its richness and complexity, its 10,000 bird species and its countless mammals and its forests and its oceans and its human civilizations and its heart and its music and its science is the product of a catastrophe. That the catastrophe was not necessary, not inevitable, not in any cosmic sense designed or purposeful, that it happened in the late Cretaceous to a world that was doing perfectly well without it and that did not need to change, and that we are here and the dinosaurs are not because of a rock in space on a particular trajectory at a particular moment in the history of the solar system. This is a humbling thought. It should be. The existence of our species, of our civilization, of everything we have built and thought and created and experienced is contingent on an event we did not cause and could not have influenced. The line in the rock marks the condition of our possibility. We exist above that line. Everything we are is above that line. The dinosaurs are below it, and they were real, and they were extraordinary, and the world they inhabited was as complex and as beautiful and as full of life as the one we inhabit now. The Triceratops moving through the Hell Creek forest on the last ordinary morning of the Mesozoic was as fully alive, as fully present in its world as anything alive today. The T Rex resting in the forest margin on that last ordinary morning had no awareness that anything was about to change. The birds in the canopy were calling. The river was running. The sun was rising over a world that had known nothing different for tens of millions of years. It did not know it was living in the last days of a world none of them knew. And then, from above, from outside the atmosphere, from a direction and a distance that nothing on the surface of the earth could perceive, the light began. Not a sound, not a tremor, just a light expanding from a point in the southern sky, brightening faster than anything that had ever brightened in the sky before, outshining the sun within seconds, illuminating the Hell Creek forest with a light that cast no shadows because it came from everywhere at once, from a fireball that was itself as wide as a small country and as bright as a small sun. Within 30 seconds, every animal in the Western Hemisphere that could see the sky was seeing something it had no framework to understand.
The T-Rex at the forest margin was looking south. The Edmontosaurus herd had stopped feeding and lifted their heads. The birds in the canopy were airborne, alarmed, circling. Within 2 minutes, the asteroid struck. The ground shook with a force that has not been matched in the 66 million years since. In North Dakota, the rivers surged and oscillated, carrying fish onto riverbanks where they had never been. The sky above was still clear and blue over most of North America. The fires had not yet begun. The cold had not yet started. The world at that moment was still the world it had always been. Damaged, shaken, alarmed, but still the world. And then, over the hours and days and weeks that followed, it stopped being that world. The fires came, the cold came, the dark came, the food failed, the great herds thinned and scattered. The last Triceratops moved through a landscape it no longer recognized, through vegetation that was dying, under a sky that had forgotten how to be blue. And in the quiet of the early Paleogene, in the cold and the fading dark of the impact winter's long end, a small mammal moved through recovering ferns, nose to the ground, following the scent of seeds buried beneath the ash. It was hungry. It was cold. It was alive. 65 million years later, one of its descendants would look up at the night sky and wonder where the rocks in space came from, and would begin, slowly and carefully and with growing precision, to figure it out. Sleep now. The world outside is old. Older than your concerns. Older than your concerns. Older than your memory. Older than the civilization that built the walls around you. Older than the language you think in. Older than anything that will happen in your lifetime, or the lifetimes of everyone you will ever know. The rock beneath you was somewhere else once. It was the seafloor of an ocean that no longer exists in that form, or the sediment of a river that has since moved or dried, or the ash of a volcano that has long since been eroded down to nothing. It has been carried here by the slow movement of the Earth's surface, a centimeter per year, a meter per century, across the enormous spans of geological time. And it will be carried somewhere else eventually, by the same slow movement. The ground beneath your feet is not standing still. It has never stood still. It is moving slowly, and it was somewhere very different 66 million years ago. Somewhere in the rock, if you know where to look, is the line. The thin, dark layer of clay, enriched in iridium and full of shocked quartz and glass spherules. The record of a single morning 66 million years ago, when the sky lit up over the Yucatan and the world changed forever. The line that runs around the entire planet, from the chalk of Denmark to the limestone of Spain to the shale of New Mexico to the sediment of the Pacific. Everywhere on Earth, the same morning is recorded. The same event, the same beginning of the end and the end of the beginning. Below the line, the Mesozoic, the forests of the Hell Creek floodplain. The Triceratops on the riverbank in the morning light. The T-Rex at the forest margin, eyes open, watching the strange light spread across the southern sky. All of it real, all of it present in its own moment, with the same solidity and weight and aliveness that the present has for you now. Above the line, everything that followed. The ferns colonizing the bare ground. The small mammals emerging from their burrows into a cold and darkened world. The slow recovery. The diversification The 10 million years, the 30 million years, the 50 million years of evolutionary creativity and ecological complexity rebuilding layer by layer into the world we know. The 65 million years that produced, among countless other things, the species lying somewhere tonight, thinking about the line in the rock and what it means. You are above the line. You are the product of everything that survived the crossing. The biology you carry, the heart beating steadily in your chest, and the brain generating these quiet thoughts is the direct inheritance of the animals that made it through. It is the inheritance of the survivors. The small, the flexible, the capable of eating whatever could be found in the cold and the dark of the early Paleogene. It was not guaranteed. It was not fated. It was not the inevitable outcome of any direction that life was moving in. It was contingent on events that could have gone differently, on a rock in space that might have missed by 100,000 kilometers, on small mammals in burrows that might not have survived, on a recovery that might have taken longer or stalled or produced different dominant groups. It was contingent all the way through, right up to the moment when the particular series of evolutionary events that produced your particular nervous system occurred. But it happened. The asteroid struck. The world changed. The small mammals survived. The recovery proceeded. The primates appeared. The cognitive expansion occurred. And here you are, thinking about all of it in the dark, connected by 66 million years of unbroken biological continuity to a small, frightened, hungry animal crouched in a burrow while the sky was dark and the world was cold and everything large was dying. Sleep now. The line in the rock holds its quiet record of what was lost and what survived, of the old world and the new world, separated by a few centimeters of dark clay that is patient and still in the rock of a planet that does not hurry and does not forget. You are the continuation of something very old and very unlikely and very much alive. The line is behind you.